So the talk today, the talk will not be focused on PKI specifically. The talk is more about how to use PKI and crypto systems and crypto primitives in order to secure systems in general, and in particular communication systems, and focusing more about what we do today in DarkMatter. So let me introduce myself very quickly. My name is Najwa Aaraj. I'm a Senior Vice President of Special Projects in DarkMatter. DarkMatter is a startup in the security space based out of the United Arab Emirates. And we have had the privilege to partner with PrimeKey on PKI and other topics as well. This slide you all know. Basically, this is how computing systems have evolved over the time. So from being focused on mainframes in 1970 to going into IoT and cyber-physical system to 2016, we can all see that connectivity has increased. Humans are relying more on the internet to do their, even on their daily life purposes. Businesses are relying more and more on connectivity, on the internet to store data, to process data, to communicate data. So do governments today. However, with this increased connectivity, basically this only means that the attacks and threat vectors and target vectors are all increasing. And along with the number of attacks, the attack sophistication itself is increasing. So there have been more than 3 billion new attacks reported in 2015, 2016. 300 million threats have also, unique threats have been reported in 2015 and 2016. And the scene is also different. So whereas before we had what we call the simple unstructured attacks, being the common attacks, and that was only 3 to 5 years ago, where one individual user was targeted in order to steal certain ID information, certain data, certain financial informations for cyber fraud, or only targeting with malware. Today, the attacks are more and more increasing into the complex and coordinated attacks. So we have heads of states that are being targeted, government leaders that are being targeted, government entities, power plants, nuclear plants, and other that are being targeted. And the purpose also is different. Basically today, all these attacks are more, they're going into how do we disrupt services, how do we steal government and confidential information, how do we distract, and also going into terrorism purposes. So given all of these attacks, and given that actually security is on top mind of almost 75% of IT professionals, this only means that companies across the globe have to work more and more into doing end-to-end secure solutions. Basically taking all the nice theoretical concepts that raise intellectual curiosity, put them into implementation, and then put them into system in order to ensure end-to-end security of such systems. And this is what a company like DarkMatter does today. So from now on in the talk, I'm going to focus more about how do we secure end-to-end communication system. We have also other communication solutions, other secure solutions that we provide, but I will only focus in this talk on secure communication solution. How do we take concepts such as crypto protocols, cryptographic primitives, cryptographic algorithms, key management, TPM, trusted platform modules, PKI that we are working with PrimeKey on, operating system security. How do we put all of this in order to ensure that we have end-to-end secure communication solution? We have a protected data at rest and data in transit, and the operating system of all the communication solutions that we are using are hardened and secure from attacks. So this slide really is when we look into secure communication solution, we look at it, as I mentioned, end-to-end. So yes, it is important to have applications at the user space that ensure secure voice, secure data communication, secure SMS, secure email, etc. But really, this is not enough. So if your application layer at the user space is secure, and then your operating system is still open and you don't have the right measures and the right countermeasures at the operating system, basically be sure that your phone or your iPad or any communication device that you are using is not secure. Hence, you see those 4 dimensions that I have in the slide. So the first one is the communication security. Basically, using end-to-end, the purpose of this is to have end-to-end secure communication, transmitted voice, SMS, data, email, and any other sort of communication that we use in our daily life and our business life today. And in order to achieve that, basically, it's common what is used is end-to-end crypto protocols. We can go through the properties that we want to achieve in few slides. Strong crypto implementation and strong crypto algorithms. We need to have a proper key management, and most likely, it's hardware rooted. And this is what companies today, like Qualcomm and others, are going towards. And improved random number generator and entropy management on a system on chip. Now, this is fine. However, we need to think also like layers down in a system. And we need to think about how do we protect operating system? How do we actually put security extensions on the operating system and the kernel in order to make them secure? By no means this list is exhaustive, of course, but certain things today that we look at and we are actually implementing in our products is how do I implement an integrity monitor at the kernel and operating system level that is constantly checking the binaries against their signatures and hashes in order to detect a malicious attack or a malicious modification of those. How do I do process isolation, either at the virtual level or at the physical MMU level, in order to isolate each of the process and then not let one being introduced in the address space and the memory space of the other one? How do we ensure secure boot? Today, we can protect the system all we want. However, if we don't have our certificate on the SOC and we will still rely on the OEMs or on the SOC manufacturer to do this whole signature checking or this whole signature chain of our bootloader and our boot sequence, we are still targeted by an attack. The data, when it lies on the system, we need to have full disk encryption using appropriate crypto algorithms. And finally and this is also related to the certificate point, is my root of trust shouldn't be in software. My root of trust shouldn't be solely relying on TEE. How do I take this root of trust, which is basically the base of the whole trust in my system, and then put it in hardware? Using an HSM, using a crypto card, using other mechanisms. This is also an architectural consideration that needs to be taken when I am to design an end-to-end secure system. Third is the management. We can have the most secure system as we want. However, if we don't have the appropriate management interface, basically we are still prone to this vector where, I give the user the phone, he is using it, I have no control over how the user is using it, where he is putting it. If his phone actually has been stolen, I have no control of this. So every secure communication solution needs to be coupled with a proper management solution so that we can do OTA device management, we can audit critical events, be it security events that we do. Even though we have all the prevention mechanisms, we need to monitor what are the events, what IPs are being accessed on a system, how are the IPs interacting, and how are they actually being monitored or prevented against with all these measures that we are putting together. And finally is the infrastructure. So the infrastructure itself, where this whole security communication or the secure communication solution are residing, also needs to be hardened. Inside the data center, all the physical security measures have to be taken. Also, anything that is being used in the server and the database, etc., needs to be properly hardened and properly managed from a security perspective. So as I mentioned, I'm going quickly through this slide. Okay, so I have it all. So one is at the top layer, the communication has to be secured like using an end-to-end secure protocols. The first thing is to define what are the security properties of the protocol that I want to use. This is the most simple protocol that you can find. This is not what we use. It's just like for presentation purposes. One is the algorithms have to be, basically we have to use solid algorithms, whether be it what NIST advocates for, what the German BSI advocates for, be it your own custom algorithms that are being developed. Security properties and bounds have been defined in the literature, have to be satisfied. Second, the crypto library has to be hardened, and I will come to explain more about this, what I mean by this in the later slides. Robust authentication and localized PKI. This is a very important factor. How do I use PKI in our system in order to do authentication, be it based on certificates that are being checked by a TTP or a CA, be it certification pinning, be it like attribute-based certification. A proper PKI has to be implemented in the system. PFS, perfect forward and future secrecy, has also to be done in a protocol that is end-to-end secure. And then at the end, there are properties that we pick and choose. Do I want anonymity in my protocol or in my protocol? Do I want non-repudiation on my protocol? Do I need other properties? This is how we design this end-to-end protocol. The second one is beyond the protocol for the communication layer is I need to ensure security of my kernel and everything that lies on my system at the hardware level. So one, in a system, we need to ensure that we have data at rest encryption. So all the data at rest has to be encrypted. Be it we use AES, XTS, we use stream ciphers, we use other modes also of AES, then data encryption has to be properly done, and the keys that are being used for this data encryption have to be properly managed. Real-time integrity monitor. Basically, all the binaries, all the device driver binaries and others have to have their they have to have the hash, they have to have the signature taken, and then we have real-time integrity monitor on the system, so that if there is any attack against them, if there is any rootkit that got placed at the kernel or the operating system level, we have a signal to the back end that this one has been compromised, and then remove it from the system. Hardened crypto libraries, this applies both at the data at transit and the data at rest, hardware rooted key management, and then finally hardened operating system and kernel. Today we have things like SE Linux, we have GR Suite, we have other memory randomization mechanisms that are being used, and all of these can be put together in order to harden the operating system and kernel. Today you have lots of also research that is being done on how do I secure my baseband processor, how do I use my virtual graphical cards, and all of this. So all of these are part of the hardened operating system and are part of protecting the operating system so that we don't have a point of entry in the phone, and then hence that becomes the weak link. So having covered all of that, I would like to dig deeper into the crypto area. So as you saw in the previous slides, a common factor across all of these measures is really the crypto design and the crypto implementation. So if we have, basically by attacking the crypto part of a device, and this is the area that is most targeted by attackers, secrets can leak, keys can leak, and then the whole device will become compromised. There are 4 areas that again, this is not an exhaustive list, but there are 4 areas that when designing a solution based on crypto that needs to be ticking the box. The first one is from a theoretical perspective, and I will leave this to mathematicians and cryptographers basically to address, is that encryption should be interactable. So basically, it's not an NP-complete problem, of course, but it should be hard enough for an attacker or for somebody who has supercomputers, and not quantum, I will leave this for another discussion, in order to go back into factoring large numbers and in order to reverse the math. And these are properties of RSA, of ECC, that we have interactable properties of those ciphers. When designing a system as well and then choosing the crypto algorithm, there should be an adequate and good enough bit level security. So when we design this solution, we say, do I want an overall 128-bit of security? Do I want an overall 256-bit of security? And based on that number that I put together, I need to choose my algorithms right, I need to choose my primitives right, I need to choose the size of the binary field right, and then put them all together in order to give me this bit level of security that I have. And this is more often than not determined by what do I think, who are the adversaries that I think will attack a system, what is the computational powers that we have, and what is the maximum bit level of security, actually the minimum bit level of security that I need to ensure in order to protect my system against those attackers. Root of trust is a very important thing in a secure system, and especially in a secure communication system. Where should my root of trust be? Do I put it in a crypto card? Do I put it in the trust in TEE, in the trust zone? Do I put it in an HSM, in a TPM? All of these have to be decided on, also based on what is the attack vectors and also this the threat scene that I think my system is placed on. And finally, and this is something I will focus on from this slide onwards, is implementation. I can have the strongest crypto algorithm, the strongest crypto primitive that I want. If I have an inappropriate implementation, and if my implementation of this crypto is not adequate, basically my whole system can be totally weakened and can be hacked into. And the most common ways of attacking a crypto implementation is side channel attacks. So this is a very, very simple example. I hope we don't find systems, basically, that still have this sort of leakage, where this picture that I have is taken from a chip and basically from a probe. It's a very cheap setup where I find the probe, I find a chip, I have an oscilloscope, and basically I take the signals from a crypto chip or a crypto system, or even on our phone. There are certain phones that are cheap phones where if there is a crypto application or a crypto algorithm running on it, if I basically take the signal with a probe, I am able to take those signals out of it. So this signal corresponds to a scalar multiplication in ECDH. And as you can see, you have two patterns that repeat themselves. This is a truncated visual that I took from my oscilloscope. You can see that you have power signals that have high peaks, and then you have power signals that have low peaks. This is, as I said, a scalar multiplication. Mathematicians or cryptographers know how the scalar multiplication happens, and then they know that basically when the bit is 1, I have an adding and a doubling operation that is happening, so basically more power is being consumed. And then when the bit of 0 of the key or of this scalar basically is 0, I only have a doubling operation. So if you try to read this in terms of what would the corresponding bit of the key or the secret be, you can tell that whenever I have a high signal, that means I have two operations taking place and the bit is 1. And then when I have a low power signal, it means that I have one operation that is happening, so the bit of 0. And then given this, and then observing more traces together, it's very easy to extract this signal. Now, you may tell me, and the same thing can happen with RSA, whether it's implementing CRT or not, so the same type of information can be deducted. So you may tell me that maybe this is a far-fetched attack, that, like maybe people don't care about it, or it's not really a real attack. No, it is actually a real attack, and this is one of many things that today when you want to do a certification, and actually the FIPS standard this year, they included SPA and DPA as part of the certification. These are things in the crypto implementation that today, in order to have a certified product, and you have to have a cryptographically strong product, you need to prove actually that your device or your system or your chip is actually resistant to SPA, simple power attacks, and differential power attacks, or correlated power attacks. So targets that have been actually included in this analysis, and where we have in the lab, we have run many experiments in order to try to extract secrets or pins from devices. So we could actually do those experiments, and successful experiments, on smart cards, on FPGAs or microcontrollers, custom processor, configurable processors, other targets. And they're actually usually when plastic is involved and tamper-resistant chips are involved, it becomes harder. But then if you are persistent in the experiment and in the analysis, you will be able to conduct the analysis. Other targets would be USBs, would be consoles, would be would be mobile phones. So all of these, whenever, if they don't have the right countermeasures against simple power analysis or differential power analysis, they can leak your secrets, they can leak your keys, and then basically you can take it. And those signals, even though when you put the probe on them, you need to be at an inadequate proximity, signals can be amplified, and even attackers that are a bit far from the device can still intercept them and do the analysis on them. Now, from a countermeasures perspective, the first layer, which is the algorithm level countermeasures, have been worked on for a long time. I mean, you have all the research that has been done by CRI, by Microsoft, and by other institutions. They have identified few countermeasures that can be put at the algorithm level in order to stop at least CPA, SPA, and then now looking more into DPA prevention and CPA prevention. So that includes introducing masking or blindness, which basically create into a randomness of how an algorithm is implemented. Constant time implementation, and basically this is, for example, to prevent against such an attack. So if two operations can actually seem to be taking the same time as one operation, this will reduce the amount of leakage that we can do whenever we have a bit of one and we're doing the multiplication, or a bit of zero that we are doing the multiplication. Pre-computations help a lot in doing countermeasures against this type of energy and electromagnetic leakage. Noise-based countermeasures, and now also we have the trend into increasing the dependencies on Boolean operations. And we see this a lot when we do operations with OTPs, when we're using stream ciphers and others, just pure Boolean operations where we cannot extract many signals in order to do the analysis, or to randomize the structure in the algorithm, so between rounds. For example, if we have an AES, and we can randomize of how this encryption over the 14 or 12 or 10 rounds is happening, and randomize the structure of the algorithm, or also randomize the data structures that are being used in order to store states of running the algorithm. And the other countermeasures are protocol level and architectural level. These are things that maybe you don't see a lot of literature around them, because this is work and this is research that has been happening not long time ago. And as a company, we're also involved in such research, and we're collaborating with academic universities in Europe on. The first one is protocol level countermeasures. So far, whenever we talk about side channel attacks, basically the thought goes on, okay, I have an AES operation, I measure the signal or the power signal when this AES operation is happening, and then I can try to extract the keys. But there is another level of leakage that can happen in any system, especially PKI-based system, is that I have a whole protocol that is happening. I have authentication that is happening. I'm exchanging the keys with ECDH or DH or any other manners. I establish the keys. I decrypt and encrypt my data. I most likely compute an HMAC. So this whole algorithm together. So this protocol can be modeled as a state machine. And the transition between one state and the other leads into leakage. So the countermeasures that I'm talking about here is that how do I put enough randomness in how this protocol is being used or it is being implemented in order to reduce the amount of leakage in my system. Certain countermeasures, one is key agility. Basically, if I am calling you or if I'm sending you a chat message, how do I make sure that I am refreshing my key per session, per message, per voice call, etc.? And this is what we call key agility that need to exist in end-to-end secure protocols. Layered security, basically, how do I take different layers of security, whether be it on the public key crypto or the private key crypto, or how do I use private key crypto in like different blobs and in a layered manner. Increased overall bit level of security. So as we move into from 128 to 256 bit level of security in a certain protocol implementation, this also should reduce the leakage. Redundant crypto operations, which creates noise and randomness in a protocol implementation, And then finally, we need to be smart about how do we choose our crypto system. Then we have countermeasures that are at the architectural layer. So you can all imagine that if I'm implementing everything in software, I will have more chances for the operations that are happening in software, they have more chances for leakage and then capturing signals that I can take and analyze using my system of equations and then come to the secrets that are being used. So a lot of countermeasures that are being used today from an architectural perspective are one, hardware software co-design, and this is what I refer to as hardware-based root of trust or hardware-based crypto acceleration, gate-level modification, chip-level partitioning, and then basically introducing physical security, tamper-proofing in order to be able to extract less of leakage from a certain platform. So finally, and this is of course open to debate, questions, or point of views, is given all these attacks, we know that we need to design end-to-end secure communication solutions. So when we want to do that, what are the things to look out for? One is the protocol has to be properly designed with the right balance of authentication, with the right balance of mixing the public key crypto and then the private key crypto and other cryptographic elements. And when this protocol is used, it's not enough to do the security proofing of this. We need to also, as a new attack vector, we need to see how there is leakage between the different states of a crypto protocol and how it's being implemented. The second point is we design everything, but everything has to be designed bottom up. So as I mentioned before, it's not enough to build security at the user space, but also we need to look at the operating system, the kernel space, and then we have to define properly the root of trust for our system. Where do we store our master key? How do we protect it? And how we do the management, the key management around that. Crypto algorithms that are being used have to have the countermeasures against SPA, DPA, CPA, timing attacks, memory attacks, or others embedded in them. We need to have strong operating system and kernel countermeasures or hardening countermeasures embedded inside, and then every system has to have the right bit level of security and, of course, the right choice of crypto primitives and parameters. So with that, I'll take any questions that you have.
Yeah, hello.
Hello.
You showed one example. This was a kind of Bleichenbacher attack, which is a very theoretical concept, and you said you did this in a lab with a smartphone or something else. How do you want to perform that in reality? You need a dedicated physical access to the smartphone.
Yes, so you need physical access. Sometimes basically you need to remove covers. It's not easy. So basically when you get a phone, you don't really know where the crypto operations is happening, right? So you need to spend time in the lab where you have the probe, you have basically the application that is being running. First, you need to locate on the chip where the leakage is happening. And after you locate, you need to take traces. Sometimes the trace is not as easy as this. Many algorithms and many implementations that you have today, yes.
No, you will need a lab for it. In this room, it will not work because there are too many signals that will destroy your
attack. You need a lab for it, yes. So we have a lab basically, and you need to have the right equipment for that, right? So you need to have the right programs, software programs. You need to have the right probes in order to extract those leakages in order to be able to do the experiments.
Okay, thank you.
Thank you. Can you comment at all on any practical attacks against the PKI portion or certificate portion of a system, or on the other end, attacks prevented by PKI?
You mean like known attacks?
Sure, known attacks that you guys have studied, or?
See, we've done attacks not on PKI. So we've seen systems where they had, for example, an RSA implementation which uses CRT, which actually it was a real a real system that we have looked at, and then it was leaking. We looked at Intel and I processors, for example, where also like we found leakage in them, and we could hack the system. We looked at certain smart card implementation which has ECC but with lower key length, where like not the proper for the scalar multiplication, they didn't have the right countermeasures, and that did. We also worked on one phone which had a secure application, what they claimed to have an end-to-end secure voice application, and then noise mixing as well, and we could attack it. So these are real-world applications and real systems that you have, and then we found a way to attack them. Now, certain ones, especially the ones that are like purely black box to us, it takes time, one, to locate where there is leakage, and second, in order to say, okay, this is using this crypto algorithm with this bit length. Sometimes it's not very easy, especially if SPA countermeasures are included. It's not very easy to detect like in a day or two. It takes more time in the lab to detect them, but then using your technique, you can eventually discover that.
What is your standpoint on or your idea on specific encryption instructions within microprocessors such as AES and I? Is that instead of using the default instruction set for crypto?
I mean, that's one thing we do, yeah. That's one thing we do, because we do the implementation and we put the right countermeasures. Like many of those like pre-existing instruction sets that are there, they don't have, especially DPA countermeasures are not there. So this is what we do in our implementations and our development.
Mm-hmm.
Yes, behind you.
I have one more generic question. How do you deal with the fragmentation within the Android ecosystem? I mean, you have here Nexus, which is more or less applies the latest updates from Google. How do you deal with most ISPs where mobile operators, they sell their devices but they never update them? They live by the feeling that within 1 or 2 years you're going to get a new one. Anyway, so
okay, so I guess your question is related more on how do we the whole hardening. Yeah, that's a very good question. So usually when we want to do this hardening, more often than not, we need to have a certain relationship with the OEM, right? So that first we need to have the source code, because we also do hardening at the level of device drivers. So this code, I mean, especially now, it doesn't get released with the AOSP. So you would need the certain relationship in order to get access to the code, and you need and to have this sort of hardening there. And as part of that, basically patches or like new code that comes needs to be updated. And then we do work with OEMs directly and not through mobile operators. Because you need to keep introduction or this like embedding of SE Linux or GR Suite or any other hardening measures happening, and then this is why you need to have this close watch on when new releases are being launched, and then to also apply your security and hardening measures on those new releases in order to send them or to patch them to your clients. Thank you.
Well, thank you, Najwa.